Alright, welcome to Chapter 6, Expressions. This is where the Python language reference gets really interesting. We're going deep on what expressions actually mean at the language level. Atoms, literals, operators, comprehensions, generators, and beyond. This is based on the Python 3.19 language reference, published by the Python Software Foundation and licensed under Creative Commons Attribution 4.0, so we're on the most current spec. Let's get into it. Here's the roadmap for the chapter. 4 main areas. First, atoms and literals. The smallest building blocks, constants, identifiers, strings, and displays. Second, primaries. The tightly binding operations like attribute access, subscriptions, slicings, and calls. Third, operators. Arithmetic, bitwise, comparison, and Boolean. And fourth, advanced expressions. Generators, yield, lambda, the walrus operator, and conditionals. Each section builds on the last, so let's go in order. Section 6.1, Arithmetic Conversions. Short but important. When the language reference says numeric arguments are converted to a common real type, it's pointing you to the numeric type section of the stdlib docs. The left column explains what that means in practice. Python promotes the narrower type to match the wider one. The right column covers the edge cases. The percent operator with strings is a special case. It doesn't follow numeric conversion rules at all. And extension types, meaning custom C extensions or third-party numeric types, don't get automatic conversion. They have to implement it themselves via their own dunder methods. Let's see conversions in action. Line 2. Result equals 3 plus 1.5. We're mixing an int and a float. Python promotes the integer 3 up to 3.0, does the addition, and we get 4.5. Line 3. We print the type and the value together. You'll see class float and 4.5. Line 6. Result 2 equals 2 plus 3j. Now we're mixing an int with a complex number. Python promotes 2 to the complex 2 plus 0j, then adds. Line 7. Print gives us class complex and 2 plus 3j. Line 10. Result 3 equals true plus 4. This one surprises people. True is a bool, and bool is a subclass of int in Python. True has an integer value of 1, so this is really just 1 plus 4. Line 11. Print gives us class int and 5. No promotion needed. Bool is already an int under the hood. Line 14. Result equals the string hello %s% world. This is old school string formatting. Line 15. Print gives us hello world. The percent operator on strings has nothing to do with numeric conversion. It's a completely separate code path. 3 takeaways. The type hierarchy is bool promotes to int to float, float to complex. Always widens, never narrows. Custom types don't get this for free. They have to implement it themselves, and string % is special. Same symbol as modulo, totally different behavior. Section 6.2, Atoms. The smallest, most indivisible pieces of an expression. The grammar block shows everything that qualifies. Line 1, true, false, none, and the ellipsis, the 3 dots. Line 2, identifiers, which are your variable names, and literals, numbers, strings, bytes. Line 3, enclosures, which is anything wrapped in parens, brackets, or braces. The 2 columns break it down further. Simple atoms are names and literals, the most primitive building blocks. Enclosures are the wrapped forms, parenthesized expressions, list displays, dicty displays, set displays, generator expressions, and yield forms. If you can't break it down further without losing meaning, it's an atom. Quick demo of all the atom types. Line 2, x equals 42. Line 3, print x gives us 42. That's an identifier atom, a name bound to an object. Line 6, print 3.14, a float literal. Line 7, print hello, a string literal. Line 8, print true, none, and the ellipsis all in one call. Notice the ellipsis prints as the word ellipsis with a capital E. It's a real singleton object. Line 11, print a list display. Line 12, print a parenthesized tuple. The 2 joined boxes drive home 2 key points. Names and literals behave differently. a name evaluates to whatever object it's currently bound to, while a literal evaluates to a new object of that value each time. Those small ints and interned strings may be cached by CPython, and the ellipsis is a real object. It's the built-in ellipsis singleton, commonly used as a placeholder in type hints and NumPy slicing. Section 6.2.1. Built-in constants. Python has 4: true, false, none, and the ellipsis. These are keywords, not just names. You cannot reassign them. The code block shows exactly what happens if you try. Line 1, false equals 123 in the REPL. Lines 2 through 5 show the error output. Python throws a syntax error right at pass time, before the code even runs. Those little carrots on line 4 point directly at false. The caution box drives it home. Attempting to assign to false, true, or none raises a syntax error. This is a compile time check, not a runtime one. Let's poke at the constants. Line 2, print type of true. We get class bool. Line 3, print type of false. Also class bool. Line 4, print type of none. Class none type. Line 5, print type of the ellipsis. Class ellipsis, lowercase e. Line 8, true plus true gives 2. Because true equals 1 as an integer, bool is a subclass of int a. Line 9, true times 5 gives 5. Same reason. Line 12, x equals none. Line 13, x is none gives true. We use is here, not double equals. That's the correct pattern for none checks. Line 16 is commented out. It's the warning. Trying to assign to none raises a syntax error. Try it in your REPL once just to see it. 3 takeaways. True, false, none, and the ellipsis are each unique singletons. Exactly one of each exists in any Python program. Bool is int, so true and false work in arithmetic. Use that carefully. And always test for none with is, never with double equals, to avoid surprising dunder EQ overrides. Section 6.2.2. Identifiers or names. When you use a name as an atom in an expression, Python looks it up. If it's bound to an object, you get that object back. If it's not bound, if it doesn't exist in any scope, you get a name error at runtime. The 2 joined boxes show both cases. A bound name evaluates to whatever object it's pointing to in the current scope chain, local, enclosing, global, or built-in that order. An unbound name raises name error. Note, this is a runtime error, not a syntax error. Python doesn't know at pass time whether a name will be bound. Both cases in action. Line 2, x equals 42. Line 3, print x gives 42. Bound name works fine. Line 5, greeting equals hello. Line 6, print greeting gives hello. Line 9, print z, which was never assigned. That raises a name error. Name z is not defined. Line 12, value equals global at module scope. Line 14, inside outer, we shadow it with enclosing. Line 15, inside inner, we define another nested function. Line 16, we just print value. Python searches local first, not there. Then enclosing, found it. So we get enclosing, not global. Line 17, we call inner. Line 18, we call outer. Line 20, outer, runs the whole thing. 3 key rules. Binding happens via assignment, import, def, class, and for. Name error is a runtime error, not a pastime one, and Python searches scopes in LEGB order: local, enclosing, global, built-in. Section 6.2.2.1. Private name mangling. This is the dunder prefix behavior inside classes. If you define a name inside a class that starts with 2 or more underscores and does not end with 2 underscores, Python silently rewrites it at compile time. The transformation rule, double underscore spam inside class foo, becomes underscore foo underscore underscore spam. There's one exception. If the class name itself consists entirely of underscores, no transformation happens, and it applies to variables, attributes, and imported names, but not to dunder names like dunder init or dunder str, because those start and end with double underscores. Mangling in action. Line 1, we define bank account. Line 2, dunder init takes balance. Line 3, self.dunder balance equals balance. That dunder balance gets mangled to underscore bank account underscore balance at compile time. Line 5, the deposit method. Line 6, self.dunder balance plus equals amount. Also mangled, consistently, inside the class. Line 8, get balance returns self.dunder balance. Line 11, ACC equals bank account 100. Line 12, ACC.deposit 50. Line 13, print get balance gives 150. Line 16, we access the mangled name directly from outside, ACC.underscore bank account underscore balance. That gives us 150. It works. Line 19 is commented out. Accessing ACC.dunder balance from outside raises an attribute error because that name doesn't exist on the object as is. Line 22. We use a list comprehension with dir to find all attributes containing balance. Line 23. The result is just the mangled name. 3 watchouts. It's not truly private. The mangled name is still accessible if you know it. The class name at definition time is what gets used, so subclasses get their own mangled names. And dunder names, anything starting and ending with double underscores, are exempt from mangling. Section 6.2.3, Literals. A literal is a hard-coded value written directly in source code. 3 categories: numeric, integers, floats, or imaginary numbers. Each is a single number token, string and bytes. These can span multiple tokens, and F strings and T strings are treated as string literals. And a note that's easy to miss: negative numbers, like -3, are not literals. They're unary operations, the minus operator applied to the literal 3. That distinction matters when you're reading the grammar. Section 6.2.3.1, Literals and Object Identity. All literals are immutable, but that doesn't mean 2 identical literals are always the same object in memory. Line 1, x equals 7, y equals 7 in the RAPL. Line 2, x is y. Line 3, true. For small integers, CPython caches them, so both names point to the same object. Line 5, x equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Y equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Line 6, x is y. Line 7, false. For large integers, CPython creates separate objects. Same value, different identity. The warning box is important. CPython actually emits a syntax warning when you compare literals with is. Use double equals for value comparison, and the boundary between small and large integers is a CPython implementation detail that can change between versions. Never rely on it. Section 6.2.3.2, String Literal Concatenation. Adjacent string or bytes. Literals are automatically joined at the syntax level. No plus operator needed. Line 1, hello space world in the REPL. Line 2, Python gives us hello world, joined at compile time. Line 4, a more interesting example, a regular string, a raw string with R prefix, and an F string all adjacent. Line 5, Python concatenates them into one string, substituting the F string variable. 2 restrictions to know. Bytes literals can only combine with other bytes literals. You can't mix bytes and strings. And T strings, the new template strings in 3.14, can only combine with other T strings. This is a compile time operation, not runtime. You can't use it with variables, only with literal strings sitting next to each other in source code. Section 6.2.4, Parenthesized Forms. The grammar shows it's just an optional starred expression wrapped in parens. 3 boxes cover the cases. Single expression in parens, just groups it for precedence, no tuple created. Comma separated, at least 1 comma yields a tuple. The parens group the items, but the comma is what creates the tuple. And empty parens, that gives you an empty tuple. This is the one special case where parens alone produce a tuple. Everything else requires a comma. Let's confirm the comma rule. Line 2, a equals paren 42 paren. Line 3, print type and a. We get class int and 42, just an integer, no tuple. Line 6, b equals paren 42, comma paren. Line 7, print type, and B, class tuple and 42. The trailing comma made it a tuple. Line 10, C, equals parent 1, 2, 3 parent. Line 11, class tuple and 1, 2, 3. Line 14, D equals empty parents. Line 15, class tuple, empty. The one case where parents alone make a tuple. Line 18, result equals parent 10 plus 5, parent times 2. Line 19, print gives 30. Parents just controlled evaluation order here. Line 22, x, y, z equals parent 10, 20, 30 parent. Tuple unpacking. Line 23, print x, y, z gives 10, 20, 30. 3 key insights. It's the comma, not the parens, that creates a tuple. Trailing comma is required for single element tuples, and parens around a single expression just control evaluation order, like in math. Section 6.25. Displays. Python gives you special syntax for building lists, sets, and dicts in line. Line 1 shows the comprehension grammar, an assignment expression followed by a comp for clause. Line 2 shows comp for, optionally async, then for, then a target list, then in, then an expression, then an optional compiter for chaining. You can either list elements explicitly or use a comprehension. The info box notes that since Python 3.6, async for is supported inside async def functions, and asynchronous comprehensions were introduced in 3.6. Quick summary of the 3 display types. Lists, square brackets, yields a new list, elements evaluated left to right, comprehension supported. Sets, curly braces, yields a new mutable set. Critical gotcha, empty. Curly braces give you a dict, not a set. Dicts, curly braces with key colon value pairs, yields a new dict. Duplicate keys allowed, but last value wins, double star unpacking supported. The aside is worth noting, DCT comprehensions need 2 expressions separated by a colon. And since Python 3.8, the key is evaluated before the value in each pair. That's defined behavior now, not an implementation detail. List displays in action. Line 2, fruits equals a list of 3 strings. Line 3, print gives us the list. Line 4, type confirms list. Line 7, squares equals a comprehension, x squared for x in range 1 to 6. Line 8, print gives 1, 4, 9, 16, 25. Line 11, matrix is a 3 by 3 nested list. Line 12, flat uses a nested comprehension, n for row in matrix, then n for n in row. That flattens it to a single list. Line 13, print confirms 1 through 9. Line 16, evens filters range 10 with a condition, only keep x where x mod 2 equals 0. Line 17, print gives 0, 2, 4, 6, 8. 3 key rules. Elements evaluate left to right. The loop variable in a comprehension is local to it and doesn't leak out into the enclosing scope. And a list display always creates a brand new list object. Modifying it never affects the original data source. Set displays. Line 2. Colors equals a set with a duplicate red. The set drops it automatically. Line 3. Print gives 3 unique colors. Order may vary. Sets are unordered. Line 4. Type confirms set. Line 7, unique lengths is a set comprehension, the length of each word in the list. Line 8, print gives the set of unique lengths. Line 11, empty dict equals empty curly braces. Line 12, empty set equals set, with no arguments. Line 13, type of empty dict is dict. Line 14, type of empty set is set. That's the gotcha right there. Line 17, primes is a set of 5 primes. Line 18, 7 in primes is true, O1, hash lookup. Line 19, 4 in primes is false. 3 watchouts. Always use set for an empty set, never empty curly braces. Sets are unordered, never rely on element position, and set elements must be hashable. Strings, numbers, and tuples are fine, but lists and dicts will raise a type error. Dict displays. Line 2, scores equals a dict with 3 key value pairs. Line 3, print shows the dict. Line 4, type confirms dict. Line 7, dupes has Alice twice with different values. Line 8, print shows Alice maps to 99. The last value wins silently. No error, no warning. Line 11. Word lengths is a dict comprehension. Each word maps to its length. Line 12. Print confirms the mapping. Line 15. Defaults and custom are two separate dicts. Line 16. Custom has size as 20 and weight as 5. Line 17. Merged uses double star unpacking to combine them. Later keys override earlier ones. Size ends up as 20 from custom, not 10 from defaults. Line 18. Print confirms the merged dict. Line 21. Prices is a dict of fruit prices. Line 22. Expensive is a conditional dict comprehension. Only keep items where the value is greater than 1.0. Line 23. Print gives apple and cherry. Two watchouts. Duplicate keys are completely silent. Last value wins with no warning. And double star unpacking order matters. Put your overrides last.